So I'm going to talk about subglacial bed topography and how we can map it using mass conservation. There may be a few slides that you may have seen before, but I thought I would go over the story with you today. So first, we already know that bed topography is a critical model input, but I want to reinforce this yet another time. And I want to talk just for like maybe 2 minutes about the marine ice sheet instability, because everybody knows that the grounding line is unstable in a retrograde bed, but not very few people, but not enough of us know why this is the case. So I thought I would spend 1 minute on this. And then I'm going to talk about conservation of mass, how we figured out by accident that we could map the bed topography using this method. And then I'll talk about BedMachine and how it's evolving. So bed topography, we've said this, so I can be quick. It's consistently ranked #1 need by ice sheet modelers. If we don't have a good bed, we cannot work on any other process, physical processes. We talk about friction is a big one, is a big uncertainty, calving, other things. We need a good bed to start with. It's really the starting point we need. Because it controls the stability of the ice sheet, it controls the stability of the grounding line. If we don't know what the bed looks like, the model is we can run the model, but it's gonna give us something that may not be realistic. Okay, and radar measurements remain sparse, and this is why we need more missions like rings. Okay, and the most critical area, of course, because of the marine ice sheet instability, is the grounding zone and the few hundreds of kilometers upstream of that zone. Okay, so the marine ice sheet instability, MISI, is not the same as the marine ice cliff instability. That's still very controversial, and we don't have clear observations of it. Marine ice sheet instability is something that's proven, that we've been observing, that we can show mathematically, so it's real. And so what's happening is when we get an ice sheet in this configuration where the bed is retrograde, which means that it gets deeper and deeper as we move inland, is that we're starting to get an imbalance between the mass that comes in and the mass that comes out. So the mass that comes in is the integrated surface mass balance over the entire area of the basin. That's the amount of ice that's added every year or every 10 years, whatever you're considering. And then the mass out is the flux at the grounding line. So we have ice speed, we have some thickness, and if we want the glacier to be in steady state and to not retreat, we need a perfect balance between the addition of mass through snowfall and the ablation of mass through flux of ice through the grounding line. And so in the case of a retrograde bed slope, if for some reason, for example, the intrusion of warm water over the continental shelf, melting the ice, we may retreat the grounding line by a few kilometers, but you see that now the mass out, we have a bigger thickness. Not only that, we also reduce the basal friction because we've retreated the ice. So that friction that was here is now gone. So we're increasing the thickness, we're also increasing the speed. You see that now our mass out is greater than the mass in. So what is our ice sheet gonna do? Our model's gonna do? They're gonna thin because we have more ice coming out than coming in. And so if it's losing mass, it's gonna thin. And as it thins, the grounding line is going to continue to retreat, and that positive feedback goes on and on and on. The only way to stop it under this scenario is for the bed to go back up. So it may be a little bump, it may be a bigger ridge, but we need something. So there is a number of caveats to that. This is a 2D view. In 3 dimensions, we may have other factors that may slow down the retreat or may stop. Even though we have a retrograde bed slope, it may not be unstable if we have lateral shear stress, for example. But in a nutshell, that's what the marine ice sheet instability is. Okay, so coming from there, I hope you're convinced that we need to know what the bed looks like. The shape will determine the stability of the ice sheet. So now moving on to models, because this is a bit how we discovered this. Models rely on conservation laws, conservation of momentum, conservation of energy, conservation of mass, and in a nutshell, if you look at how the ice can potentially change density through compressibility or thermal expansion, overall, if we look at all the conditions that the ice is exposed to in Greenland and Antarctica, we expect the density to vary by less than 0.5%. So we can consider the ice as an incompressible material. So the complicated conservation of mass can be reduced to a velocity that's divergence-free. And that's used by all models. All models use some form of this. And classically, what we do is we depth integrate this equation over between the bottom of the ice and the surface of the ice, and that gives us an equation for what the thickening rate should be at every point. And so the thinning rate or thickening rate is equals to minus the flux divergence. That's basically looking at how much comes in versus how much comes out at every point, plus how much we're adding as snowfall and how much we're removing as basal melt under floating ice. And that equation works really well. That's how we've been able to map basal melting under floating ice shelves. So we're using the same equation, but we're moving dHdt on the other side to determine the basal melt, which was one of the terms in that equation of conservation of mass. And by looking at the flux divergence and subtracting the surface mass balance, we can map the bottom melt. So it works very, very nicely. The problem is when we take that same equation and applying to grounded ice, it's, well, we can do this at the scale of the entire ice sheet, of course. But when we look at grounded ice, you see that we still have a very strong signal that's definitely not realistic. So what I'm showing here is just this term, the flux divergence. So you see that the flux divergence here has a strong signal, and that's because of the melting rate. But over here, there is no reason really for that flux divergence to be more than a couple of meters per year, not 50 meters per year. So there were lots of ideas when we found this. The first one was that we should use full Stokes because maybe our model is too simple and the flow is actually three-dimensional, moving around bumps. And if we were to actually use the real three-dimensional velocity, these artifacts would disappear. And so we did. We tried full Stokes modeling, and you see that it looks pretty much the same as this one. So the problem was not that our physics was too simple. The problem was that the bed topography was not right. And this is not, so this is 79 North in northeast Greenland. We see this everywhere. If you take an INSAR velocity and some ice thickness from typically Kriging, and you combine these two terms to look at the flux divergence, you see that we have over fast-flowing areas, we reach magnitudes of plus or minus 100 meters per year, sometimes more. So if you run your model with these two fields as initial conditions, your initial dHdt, so thinning or thickening rate, will look like this. So your model is not going to be any helpful in terms of predicting the future because it's being driven by inconsistencies between these fields that we use in the conservation of mass. So the idea was to try to say, well, we know what dHdt looks like. We have observations from ICESat, now ICESat-2 or Cryosat. Let's try to figure out what the ice thickness should be or the bed topography should be so that this equation is satisfied and the dHdt looks like what it's supposed to be. So we're just switching these two terms, and our unknown now, instead of being dHdt, is h, the ice thickness. So this is what the equation looks like. We're solving for ice thickness such that the flux divergence is equal to the sum of these terms, and we need boundary conditions. So typically, we impose the ice thickness over the inflow boundary. And it's a transport equation. So what this means is if you know, I don't know what, oh, the animation is working now. If you know the ice thickness here, and if you know where the ice is going, you can figure out, you can propagate that forward and determine what the ice thickness should be all the way to the ice front. So that's on paper. In practice, there are regions where it doesn't work so well. So what we added to this was a minimization problem, because we need to know, there are places where we know the ice thickness. We want to minimize the misfit between what's measured by a radar and what's modeled through the conservation of mass, and we want to make sure that the two match. And by tweaking a little bit our input data, we're able to make it work. So that's Upernavik. That was before Operation Icebridge. There was basically no ice thickness measurements. After Operation Icebridge, we had a lot more, but now you see that with the usual techniques of Kriging, it doesn't look quite right. We had deep points where we had measurements, and then in between, the bed would go back up because the interpolation method are generally isotropic, and they're not aware necessarily that this should be a continuous feature. With mass conservation, we have that information by looking at the velocity. We know where the ice goes. So if it's deep here, because the ice continues to move in this direction, the model automatically will know that it has to remain deep as we go forward. So that's the method that we used to make BedMachine, and something I should already tell you is that this method works primarily in regions of fast flow, where the ice velocities is above, I say 50 meters per year. Sometimes it works well even below that, but generally it's not going to work in the interior. In the interior, you can still see artifacts in the maps. Maybe I shouldn't show you where they are, but they are due to the fact that we can't use mass conservation there, so we use standard techniques. But in regions around the coast where it matters the most for ice sheet models, we're able to apply this method. And as time goes, we get more and more data from different missions. So I'm super excited about rings. And we can update BedMachine fairly easily. I mean, it takes a bit of time, but it can be updated fairly quickly. So I'm just going to show you a couple of examples of what we can do with it. This is BedMap 2, which was a fantastic product compared to the previous one. With mass conservation, we are able to get finer details. And these details, for those of you that are a bit far, might not be easy, but we see that the grounding line that's shown here with different colors is following the topography pretty well. These regions are a lot more blurry in BedMap 2 because of how the bed is mapped. So we're able to pick up more details that do matter for models and for future projections. In some regions, we found big ridges right upstream of the grounding line. So everything that's green is above sea level, and what's blue is below sea level. And in this region, there was no data. So if you don't know what it is, with a simple interpolation, it's going to tell you that the bed has to remain is below sea level all the way. If with mass conservation, we're able to capture that ridge, and so if you run your model, this one is going to be a lot more stable because the grounding line may retreat, but then will be stopped on that big ridge. In some few cases, like 99% of the time, the radar data is beautiful and perfect. But in some cases, what happens is that we have a line here where there is assumed to be a positive identification of the bed. So this is the surface here. The top, the black line is the surface, and this is the radar pick. So here it's saying that there shouldn't be any trough. Mass conservation will be, I'm trying to match that data, but there is no way I can fit it. So it gives us a clue that maybe this pick was not right. So again, it's like maybe 1% of the data, but it helps identify these bad bed picks in a few instances. Okay, for the sake of time, I'm going to skip that one, but in regions where we don't have anything, it can provide a first estimate, and that was the case for Denman. That's very, very deep. Apparently, if you look at, it's a big basin, and it's drained over a very narrow area, so it has to be deep in order for the ice to be to reach the coast. So okay, I'm going to skip that. But surprisingly, every time I say I'm going to skip that, and I talk about it. But surprisingly, the bed topography that we get through mass conservation is fairly consistent with the retreat of the grounding line. So, I'm always worried about the mapping over here because it's very far from the last measurement. Is it worth anything? I don't know. But what we see here is that the grounding line has been retreating over some sort of canyon here that was inferred by mass conservation, and they seem to be in good agreement. Okay, Frank was in the room, so I wanted to show Le Roi-Baudouin ice shelf. And so that's BedMap 2, that's BedMachine, and again, you see this long trough that's kind of stopped in a few places in BedMap 2. So for models, if you run your model with these, the grounding line may stop here, whereas in this model, it may continue to retreat if we get ocean warming. Okay, I'm almost there, I promise. So going forward for rings, in terms of what we need for mass conservation is a cross-flow lines, because they constrain the entire flux of your system. If you get just one flow line, it's going to help that flow line a lot, but on the sides, you won't be able to constrain that flux. So anything across flow is great. There are many regions. I think people have done an amazing job in the Amundsen Sea embayment, but in other places around the coast, we have to look at where we're missing data. This is just an example of close to Brunt Ice Shelf, Stancomb Wells, and Slessor. We don't have a ton of data. So getting any data in that sector would be amazing. And so I think this is something we're going to work out together, identifying where we have data gaps and where the velocity is high, because that's where we can improve the bed topography using mass conservation. Here, we have no chance. Like the flow is too slow. Mass conservation is not going to be an option at this point. In some cases, last thing I want to say is we can run mass conservation backwards. If there is a region where we have a very good pick, we can use the same equation but with a negative velocity, so we can move in the other direction and improve the bed topography upstream instead of downstream. Okay, so my conclusions. Bed topography is a fundamental input for models. I'm sure Felicity is going to talk about it, and hopefully we'll have the same message. It helps to determine which sectors are vulnerable to warming, and of course, without a bed topography, you can't predict the future. The grounding zone is particularly critical because that's where the marine ice sheet instability may develop. So we need to know the bed topography in the grounding zone very accurately, and a few tens or hundreds of kilometers upstream. More measurements will further reduce that uncertainty, not only in mapping, but also in projections. Because as you saw in Alex's talk, if you reduce the uncertainty in the bed topography, you automatically reduce the uncertainty in predictions. So mass conservations, they provide more fine-scale details, they preserve troughs and fjords, and sometimes, in some cases, they help identify poor bed picks. Only reliable and fast though, and BedMachine is constantly updated. The next release will include the new version 2 IPSCO and other measurements that have been collected. Thank you.